Ever wondered what don't cares in digital logic are? Well, they're not some laissez-faire attitude to circuit design, but rather an ingenious tool to optimize and simplify our digital systems. In the realm of digital logic and circuit design, don't cares, often marked as CAW, refer to special conditions where the actual output value isn't crucial or doesn't affect the circuit's functionality. Picture this: you're crafting a truth table or a Carnot map, and you come across input combinations where the output value isn't specified or doesn't matter. These are your don't cares. They're like wildcards, giving you the flexibility to choose the output value for that specific condition. By utilizing these don't cares, we can simplify Boolean expressions, optimize circuit designs, and reduce overall system complexity. Intriguing, isn't it? Now let's delve deeper into the concept of don't cares and their importance in digital design. Now, what exactly does the term don't care mean in digital logic? Well, let's break it down. In the world of digital logic and circuit design, there's this concept of don't cares. They are exactly what they sound like. Situations where we simply don't care about the output value. But why is that, you might ask? It's not because we've suddenly become negligent in our digital designing duties. No, it's because, in these specific instances, the output value doesn't affect the overall functionality or performance of the circuit. So when we talk about don't cares, we are referring to particular combinations of input values for which the output value is not specified, or quite frankly doesn't matter. These are not random occurrences. They are identified during the design process based on the system's requirements and functionality. Don't cares are like the wildcard entries in our design process. They provide us with a certain level of flexibility. When a specific combination of inputs is a don't care, it means that we, as circuit designers, have the liberty to choose the output value for that specific condition. It's like having a joker in a pack of cards. It can be used in whatever way best suits our game strategy. And what's our game strategy here? Simplification. Yes, don't cares play a crucial role in simplifying Boolean expressions. They enable us to group adjacent cells, also known as minterms in Carnot maps. This grouping leads to a reduction in circuit complexity, optimizing our design and making our lives a tad bit easier. So, don't cares aren't about carelessness or indifference. They're about flexibility and strategic simplification. They're about making the most of our design process, about optimizing and streamlining circuit designs. In essence, don't cares provide us flexibility and freedom in circuit design. Why are don't cares significant in digital design? Well, they are like the wildcards in a deck of cards, providing an extra level of flexibility. When you're designing digital circuits, you often encounter them while crafting truth tables or Carnot maps. These are the places where the output isn't critical and hence the term don't care. Think about it this way. If you're putting together a complex puzzle, you might come across pieces that could fit in more than one place without affecting the overall picture. These are your don't cares, the pieces that give you room to maneuver. In the world of digital circuit design, these pieces can help you simplify Boolean expressions. Yes, you heard it right. Don't cares are incredibly useful for simplifying Boolean expressions. They allow us to create larger groups of adjacent cells or minterms in our Carnot maps. This leads to a more straightforward Boolean expression, which in turn translates to a less complex and more efficient digital circuit. Now you might wonder why we would want to simplify Boolean expressions in the first place. The answer lies in the inherent complexity of digital systems. As these systems grow larger and more complex, the Boolean expressions representing them can become quite unwieldy. The presence of don't cares allows us to reduce this complexity, making the design process more manageable and the resulting systems more efficient. Moreover, don't cares can be beneficial in situations where certain output values aren't critical to the overall system behavior. In such cases, these conditions can be treated as don't cares, providing the designer with additional flexibility. So, the next time you come across a don't care in your digital design journey, remember that it is not just a placeholder or an anomaly. It's an opportunity for simplification and optimization, a tool that can help you design more efficient digital circuits. As you can see, don't cares are quite handy when it comes to simplifying and optimizing circuit designs. How do we implement don't cares in digital circuits? This is an intriguing question that can truly demonstrate the power of don't cares. Don't cares, as we've established, provide a level of flexibility that allows us to optimize our digital circuits. Imagine you're a painter, and don't cares are like the white spaces on your canvas. They're undefined, allowing you to fill them however you see fit to create the most elegant design. The real magic of don't cares lies in their ability to simplify Boolean expressions. This is where Karnaugh maps come into play. For those unfamiliar, a Karnaugh map is a tool used in digital logic design to simplify Boolean algebra expressions. It's essentially a visual representation of a truth table. When we plot our function on a Karnaugh map, the don't cares are treated as additional cells. They're like wildcards. They can be either a 1 or a 0, depending on what best suits our needs for simplification. By grouping these don't care cells with adjacent cells, we can create larger groups. And in a Karnaugh map, larger groups mean a more simplified Boolean expression. Let's take an example. Suppose we have a function with certain input combinations defined as don't cares. We plot this function on a Karnaugh map. Now we see that by treating these don't cares as either 1s or 0s, we can group them with adjacent cells, resulting in a larger group. This larger group then simplifies to a more streamlined Boolean expression, reducing the complexity of our digital circuit. So you see, don't cares are not just about ambiguity or flexibility. They're a powerful tool that we can use to our advantage. They allow us to reduce the complexity of our circuits, making them more efficient and easier to implement. But here's the best part. While we're simplifying and optimizing, we're not compromising on functionality. The system still performs as expected, only now it's leaner and more efficient. With don't cares, we can reduce circuit complexity without compromising functionality. How fantastic is that? Can we see an example of don't cares in action? Absolutely. Let's dive into some real-life instances where don't cares play a pivotal role in optimizing digital circuits. Let's start with a digital control system. Imagine you're an engineer working on a complex control system that regulates the temperature in a greenhouse. The system has many states, each representing a different combination of inputs like the current temperature, the time of day, and the humidity level. But there are certain states where the output doesn't really matter. For instance, when the greenhouse is empty, the exact temperature is not critical. So, you as the designer have the flexibility to choose the output value for these states. These are your don't cares. Another example can be a digital watch. The watch displays time in a 24-hour format. Now consider the tens digit of the hour display. It can show 0, 1 or 2, but never 3 or beyond. So in this case, the inputs 3 to 9 are your don't cares. They will never occur. And even if they do, due to a glitch, it doesn't affect the overall system behavior. You can use these don't cares to simplify the circuitry of the watch and make it more energy efficient. Now let's consider a more academic example. Think of a two-variable function. Here the function could have a don't care condition, often represented as x. This x is treated as an additional cell in a Karnaugh map. It can be grouped with adjacent cells to create larger groups, thus simplifying the Boolean expression. This simplification can lead to a more efficient circuit design and reduce the overall complexity of the system. In all these instances, whether it's a greenhouse control system, a digital watch, or a two-variable function, don't cares provide the flexibility to make more streamlined and efficient designs. By identifying and utilizing these don't cares, designers can achieve a balance between functionality and simplicity in their circuits. These examples showcase how don't cares can be utilized to optimize and simplify digital circuits. So the next time you're working on a digital design, remember to look out for those don't cares. They might just be your ticket to a more efficient and optimized design. Let's summarize what we've learned about don't cares. These are special conditions in digital logic and circuit design where the output value isn't crucial or doesn't affect the functionality of the circuit. They're like the wildcards of digital design, offering flexibility in optimizing and simplifying circuit designs. We've seen how they come into play in creating truth tables or Karnaugh maps. Remember the example of a digital control system where certain states or conditions didn't explicitly define the output? That's a classic case of don't cares in action. They're identified during the design process based on system requirements and functionality, and they can be grouped with adjacent cells in Karnaugh maps for more aggressive simplification. Essentially, don't cares are your secret weapon in creating more efficient and optimized designs, striking a balance between functionality and simplicity in your circuits. Remember, don't cares are your secret weapon for achieving optimized and efficient digital designs.